Let's see some examples. Let's say that I have a function f of x, which is x to the power of 5, and I want to calculate the derivative. I know that f prime of x is going to be 5 times x to the power of 4. Therefore, I know that I can write that the integral of 5x to the power of 4 in dx it's equal to the original function x to the power of 5 plus c. This is valid, of course, with any type of c. I can choose also another c, for example, c prime, where c prime is just something else related to c. For example, I don't know, c divided by 5. I can do that. The function here, the result includes a constant, and this constant can be anything really. Another example, of course, can be if we have x to the power of 10. In this case, we know that the integral of x to the power of 9 will just do the job, right? So we know that the antiderivative is going to be x to the power of 10 divided by 10 plus a certain constant. Notice that the constant, I can call it c, I can call it k, I can call it as I want. Another way to look at it is that this is a fantastic way actually of checking if I'm doing things right, because I can take the right hand side here and I can derive that with respect of x. So using this notation, I can just derive x to the power of 10 divided by 10 plus the constant. And if I do things right, so I am lowering the exponent, right, 10, and then I have as power 10 minus 1, so 9. I have divided by 10, and then the derivative of the constant is 0. So I find again, okay, the function that I started with as integrand here. Now I can go on, right? I can actually, in general, find out that if I have an integral of x to the power of n in dx, then the general antiderivative is going to be x to the power of n plus 1 divided by n plus 1 plus a certain constant c, where c belongs to R. This is valid if n is different from minus 1, and we will see it very soon. Now, the same apply for n less than 0. In this case, n has always been an integer and positive. But let's assume that we have an integral of x to the power of minus 5 in dx. Well, I can use the formula exactly with this n, the one that I just wrote above. Simply, the exponent is going to be now minus 5 plus 1. So it's going to be minus 4 divided by minus 4 plus a constant. So I can write it as, I bring this minus in front of my fraction. So I'm going to have minus x to the power of minus 4 divided by 4 plus c. And I can also rewrite this if I want as, instead of having x to the power of minus 4 in the numerator, I can write it in the denominator. So I'm going to have minus 1 over 4x to the power of 4 plus c. These are all equivalent way of writing this result. And again, I could check this result just deriving the result and getting the integrand function. In the same way, of course, the integral of x to the power of minus 2 in dx, again, it's going to give me x to the power of minus 2 plus 1, which is minus 1, divided by minus 1 plus a constant, k belonging to R. I forgot here, c, it's belonging to R. And then in this case, I'm just going to have a minus 1 over x plus k, where k is just a real number. The same applies to rational numbers. So let me erase this first part over here. And let me explain what I mean. So let's assume that you have a rational number, so a number that can be written as p over q, where p and q are integers. These are the rational numbers, for example, 2 over 3, 1 over 5, or something like that. So you have an integral of x to the power of, for example, 3 over 5 in the x. How do you do that? You do exactly as we did before. So you apply the formula and you will find that your antiderivative is x to the power of n, and in this case it's 3 over 5 plus 1, and then divided by 3 over 5 plus 1, plus a constant, where the constant again is belonging to r. It's really necessary to write that, okay? Now, this one has to be simplified a little bit, so it's important that actually we work out the exponent, which is the same as the denominator. So we have that 3 over 5 plus 1, it's actually equal to, common denominator it's 5, so it's 3 plus 5, so it's equal to 8 divided by 5. So actually this integral is equal to x to the power of 8 over 5 divided by 8 over 5, that I can also rewrite as 5 over 8 times x to the power of 8 over 5. Yeah, I forgot here the constant. This is a bit more nasty, right? But somehow that's how it is. If I derive again this result, I will find exactly the integral. A famous, a more common, of course, integrand, it's the square root, right? The square root, I can rewrite it as x to the power of half in the x. And now my result is going to be x to the power of half plus 1, which is 3.5, divided by 3.5 plus a constant, where the constant it's a real number.